Weinstein, can you hear us?
Yes, I can. Can you hear me?
Yes, sir. Shall we start? Are you ready to start?
I'm ready when you are. Yes.
Okay, sir. I'll just give a brief introduction, and then we start. Um, folks, PAC is proud to host a guest lecture by Dr. Aaron Weinstein as the first event in our Cosmic Voyage 2026. Dr. Weinstein is a professor of physics at Caltech and the head of the astrophysics and data analysis group at the LIGO laboratory at Caltech. He'll speak on gravitational waves and their detection using advanced detectors like LIGO. He'll also give us an idea of the LIGO project, including LIGO India. On behalf of PAC, I thank him for agreeing for this talk and request him to take over first.
Okay, very good. You can hear me, I hope. Hi, everybody. It's oh, do you see the screen as well? Do you see the black holes orbiting each other?
Yes, yes.
Okay, very good. Yeah, it's early in the morning here in California. I hope things are okay over there. How's the weather in India?
It's pretty pleasant here right now.
Excellent, excellent. Okay. All right. So I'm going to give you sort of a big picture overview of gravitational wave science, and in particular, the LIGO project. And I will uh, I will leave room for questions. So if you have any questions, feel free to interrupt me. And I will just start right about now if I can get the screen to advance. Let's see. There we go. So thank you very much for inviting me. It's a pleasure to be here. I wish I could be there in person. I'll be in India at the end of April at Pune at Ayuka in Pune. Anyway, so let me start from the very beginning. These guys, I assume you remember who they are. Actually, I am assuming that you guys are mostly engineering students, not so much physics, but this is a physics and astronomy club. So maybe I'm starting just a little bit too elementary, but I'll remind you that on the left is Isaac Newton, and wrote down his force laws, including the law of gravity. And he noticed, but it was noticed by lots of people, that the same mass appears on both sides of the equation. You can cancel them out. And that leaves an acceleration due to gravity, which is independent of the object that is being accelerated. And that gave Einstein the idea that that acceleration is due not so much to the properties of the object itself, but just where it lives in space. And that gravity was a curvature of space that would affect everything. And that means everything, even beams of light, um, as they move through that curved space. Was a radical idea. And on the right is Einstein's equations. We'll get a chance to talk about them in a little bit more in a second. So the picture on the right that you see here is an embedding diagram, imagining space as being two-dimensional. You've probably seen a picture like this before. This is in the center is, let's say, the sun. And in this picture, it's distorting the space-time around it. And that test particle, the blue circle, which imagine is the Earth, is moving in a straight line through curved space. And that shortest straight line path is essentially a Keplerian orbit as described by Newton and Kepler. A little bit different, and that difference is measurable and has been confirmed as due to is better explained by the curvature of space-time than by Newton's laws. Now that's a static picture, but on the lower right, you see a dynamic picture of two sun-like objects orbiting each other. And as they do, a distant observer feels a very gentle strengthening and weakening of the gravitational field that it feels from a distance. And that information is carried at the speed of light from the source to the observer as gravitational waves. And that is what Einstein predicted way back in 1916. And it took 100 years to confirm that prediction. So the idea is that masses that accelerate, for example, in a binary orbit, will radiate radiation, which are ripples of changing gravity or changing space-time curvature in space and time. And these are gravitational waves. They're described by Einstein's field equations. On the right there, you see G mu nu is a space-time tensor, and T mu nu is as well. And G mu nu describes the curvature of space and time. And T mu nu describes the sources that source that curvature or the changing curvature. And over in the front, there's a bunch of constants, 2 pi g over c to the fourth. Those are just conversion factors. So the idea in Einstein's equations is that the curvature of space-time is sourced. Here, I'll use maybe you can see this. The curvature of space-time is sourced by matter and energy, including its motion. And the curvature of space-time causes matter and energy to move in a different way because it's under the influence of a gravitational field. So matter and energy curve space-time, and space-time curvature tells matter and energy how to move. And that's Einstein's equations in a nutshell. Now, if there's no source, if you're far away from a source, a radiating source, T mu nu is 0, and the Einstein's equations are G mu nu equals 0, which looks like a very simple equation, but it's not. It's an extremely complex space-time nonlinear differential equation, strongly coupled and correlated. And so there are only a few solutions to it. For example, solutions that describe the curvature of space around an object like the Earth or the Sun, or a black hole, or also the curvature of space-time in cosmology, the entire curvature of the universe. And there really aren't that many other solutions to the equation that have been worked out analytically. Harder problems like how the source's gravity has to be computed via supercomputers. I'll show you an example of that in a bit. Okay, now space-time curvature is usually very weak. Around in our solar system, it's weak but measurable. But it's a tiny effect. It's a strong effect, essentially in two places: the universe in the early moments of the Big Bang, and near or in the horizon of black holes. And this is where general relativity becomes strongly nonlinear and of great interest to physicists. So this is why we want to study it. Now, we don't want to get too close to black holes or the Big Bang. It's not possible for us to do that anyway, but if we did, the tidal forces would destroy us. So we don't want to get too close. But strong sources will emit gravitational waves that we can detect from far away. They get very, very, very weak by the time they reach us. And they are a probe of what's happening in the strong field, highly dynamical region where general relativity, or whatever the true theory of gravity is, gets really interesting. So that's really our goal as physicists, is to understand strong field, highly dynamical, rapidly changing gravity. What gravitational waves do in the context of general relativity is they stretch and squeeze space. So here's two objects separated by a distance L, and the space between them is changing due to a passing gravitational wave by an amount delta L. The ratio delta L to L is called the strain. It's a dimensionless quantity, and it's what characterizes gravitational waves. You can see a wave equation written just below it. And if the wave is propagating into the board, into the screen, then it's doing the stretching and squeezing of space in one direction, and it's squeezing space 180 degrees out of phase in the other direction, perpendicular to the direction of motion. Gravitational waves are transverse waves. They stretch and squeeze space between perpendicular to their direction of motion. They propagate at the speed of light, even though they have nothing to do with light at all. In fact, both light and gravitational waves travel at the maximal speed allowable by space-time. In quantum language, you can describe gravitational waves as carried by gravitons in the same way that electromagnetic waves are carried by photons. There's a couple of differences. One similarity is that the graviton is massless in general relativity. That means that the waves travel at that maximal speed, which we call the speed of light, but I prefer to call it the speed of gravity. These are transverse waves, and they're described not by vector quantities like electric and magnetic fields, vector fields, but by space-time tensor properties. Okay? So a space-time tensor has 4 dimensions, 1 of time, 3 of space. A tensor is a 2x2 matrix it can be represented by that 2x2 matrix down here. And this is the strain changing the distance between objects perpendicular to the direction of motion. The direction of motion is the z direction. That's the bottom row and the bottom column. The time direction, 0 also, but transverse to the direction of motion, there are 2 polarizations. We call them plus and cross. That's the fundamental physics of gravitational waves in the context of general relativity. More equations. One thing that you can do is calculate if you had a binary of 2 massive objects, like stars, for example, orbiting each other at a distance of capital R and at an orbital frequency of omega orbital, you can calculate the strain that an observer would see at a very, very distant observer at a distance of little r here in the denominator. The strain falls off like 1 over r. It's an amplitude. The energy falls off like 1 over r squared, same as gravitation, as electromagnetic waves. But what you see is that the strain, even if you put 2 very massive objects, like 2 objects the mass of the sun, very, very close to one another, something like hundreds of kilometers apart, they'll be orbiting each other at a good fraction of the speed of light. And even if they're placed very, very far away, like a megaparsec, like the next galaxy over, the Andromeda galaxy, you'd get strains that are very, very tiny, unmeasurably tiny, almost unmeasurably, unless you build an extremely sensitive measuring device like LIGO. And what it's going to do, in addition to help us learn about strong field gravity, it's also going to help us learn about the astrophysical sources themselves. And what we know about astrophysical sources up till now have come from electromagnetic radiation in all the various bands of the electromagnetic spectrum. The visible light, we see stars mainly in the nearby in our Milky Way galaxy. In the infrared, we see star-forming regions in our galaxy. This is in galactic coordinates. So the galactic plane is along the equator in these pictures. We see star-forming regions, brand new stars being formed. If we look in the microwave, we see the cosmic microwave background. If we look in gamma rays, we see a lot of sources, high energy photons in the Milky Way, but also extragalactic, very, very far away galaxies, so far away that they don't trace the Milky Way at all, in enormously energetic bursts called gamma ray bursts. Over in the lower right is the gravitational wave sky. When this slide was made 10, 20 years ago, we had no idea what it looks like. Now we're beginning to know. And it's starting to look a bit like those GRBs, those gamma ray bursts. Points very, very far away, emitting enormous amounts of energy, and telling us about not luminous matter, but dark matter, like black holes. And that opens up a whole new window on the universe, very different from what we can see using electromagnetic radiation. In fact, just like electromagnetic radiation, gravitational waves come in a broad spectrum, but this time at much lower frequencies than you would with electromagnetism, because they're emitted by very massive objects that can't move as fast as electrons on the surface of a hot star, for example. So they're moving slower and they emit gravitational waves at lower frequencies. Way here on the right is somewhere between 1 hertz and 1,000 hertz. And that's the regime in which you can detect gravitational waves on the surface of the Earth with ground-based laser interferometers like LIGO, which I'll talk more about. And I could talk forever about all these other ways of detecting much lower frequency gravitational waves, including pulsar timing, when we have what we think is a signal from supermassive black hole binaries. Hard to tell right now, but it's the beginning. But most of our signal, most of our gravitational waves are detected with these ground-based detectors, like LIGO. Okay, there are two LIGO detectors in the United States. LIGO is the Laser Interferometer Gravitational Wave Observatory. These are laser interferometers that are very long baseline, 4 kilometers long, in the shape of an L. We have one in eastern Washington State, in the upper left here of the United States, and one here in southern Louisiana near New Orleans. We will put a third in India. It's in the process of being built right now. It's a big project. It's such a big project that we can no longer show pictures of all the people involved in the LIGO scientific collaboration. We can barely fit the logos of their institutions in here. Somewhere in here, I think I should have looked for it earlier. Somewhere in here, we could find at least one or two, or probably several institutions in India, including IUCA. Okay, but we're building more. We have the two detectors in the United States, Advanced LIGO, Hanford and Livingston. There's a detector outside of Pisa in Italy called Advanced Virgo. The geodetector is in central Germany. It's no longer online. There's a detector called Kagra in the Japanese Alps in the Japan Sea. Kind of a few hours of fast train from Tokyo. And we are currently building LIGO India in Maharashtra. And it's starting to be built, even as we speak. Here's what they look like in aerial photos. You can see their scale. So for example, here in LIGO India, LIGO Hanford, this is the central part of the detector. This building over here is 2 kilometers away, and this building over here is 4 kilometers away. And similarly, the other arm, we call this the X arm, and this is the Y arm. And here's Geo in a cornfield in Europe. And I'll show you some more slides, pictures of these detectors later. The detectors are very simple to look at them at the start. They're insanely complex devices in order to be as sensitive as they are. Indeed, they're the most sensitive measuring devices ever built, and that's reflected in the complexity of their design and operation. I'm simplifying things tremendously here. We have a laser. It impinges upon a beam splitter. Half the light goes this way, bounces back and forth between 4 kilometer long separated mirrors, laser mirrors, which we call test masses, because they're the things that will have their distances change when a gravitational wave goes by. And then that laser beam comes back. Half that laser light, however, goes up to the other arm, the Y arm, bounces back and forth hundreds of times, going something like hundreds of kilometers before coming back to the beam splitter and recombining. In the absence of a gravitational wave, all the light comes back to the laser and gets recycled back in. In the presence of a gravitational wave, stretching space in this direction and squeezing space in that direction, some laser light comes through here, through what's called the signal recycling mirror, to a photodetector. And that is how we transduce gravitational waves into laser light at a photodetector at optical frequencies. Somewhere between, so the laser light is at optical frequencies, and the signal is at audio frequencies, between about 20 hertz and 2000 hertz. Okay? This is the strain noise, the noise in the detector that prevents us from detecting gravitational waves, unless they're louder than the noise. So a signal up here would be detectable, and a signal down there in the frequency domain would not be detectable. Let's see if this plays, and I hope it even has sound. Do you hear the sound?
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our Sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
Well, that pretty much tells the story. However, I'm going to give you more detail on some of the physics that we do with this. So one thing is that similarly to electromagnetic radiation from astrophysical sources, gravitational waves come in multiple different sources. One of them is the one you've just heard about, coalescing compact binaries. Compact refers to black holes or neutron stars, and coalescing refers to the fact that they start out as stars orbiting each other at a distance, and then they lose energy and angular momentum through the emission of gravitational waves until they approach each other in an in spiral, and then they merge together into a single black hole, which shakes and rings down the way a bell rings down when you shake it. So that's in spiral, merger, and ring down. And these are strong emitters of gravitational waves. There are other sources. These are so strong that we can detect them from distant galaxies, which is important because this kind of thing happens in our galaxy, the Milky Way, only once every 10,000 years or 100,000 years. We're not going to wait for it to happen in our galaxy. It would be very, very strong, but not strong enough to hurt us, but strong enough to be easily measured. But if it's far, far away in galaxies hundreds of, billions of light years away, we can still detect it. By contrast, these other sources are weaker and haven't been detected yet at all. One of them is a spinning neutron star in our galaxy. The Milky Way galaxy has hundreds of millions of spinning neutron stars. If they have a little mountain on them, that will cause them to emit a sine wave of gravitational waves that will be always on. We look for these, we haven't detected them yet, but I think we will soon. If there is a collapse of a very massive star in our galaxy, a core collapse supernova, then it will produce an enormous amount of light, an enormous amount of material, an enormous amount of gravitational waves, and neutrinos, all of which we will be able to detect. Unfortunately, this only happens, well, once every 100 years or so in our galaxy. Could happen at any time. And when it does, you will hear about it because we'll be detecting it in a lot of different ways. But has not happened yet while LIGO has been turned on. In fact, the last core collapse supernova was observed hundreds of years ago. Finally, there's the analog to the cosmic microwave background called the cosmic gravitational wave background. Doesn't look like this. This is the cosmic microwave background, but that is also detectable, and we hope that we'll be able to do that very soon as well. It's also always on and at all frequencies, so it's not just a single transient burst of gravitational waves like you just saw in the last video. In fact, let's see, the upper two are bursts, and the bottom two anticipated sources are continuously always on. I'm going to focus on the compact binary coalescence because that's what we've detected so far. Okay, now you can describe these in two different, you need two different kinds of tools to describe them theoretically. So theoretically, for black holes, they're described entirely in terms of space-time curvature, which means you need to solve Einstein's equations in the presence of sources, which is very difficult to do, and we can do it for signals on the lower left. On the upper left, you can see a visualization of a signal from such a system. Calculated in a supercomputer, you can see all kinds of interesting features. The black holes up here, their orbits next to them. This over here is a two-dimensional representation of the space-time that they are occupying. You can see these deep wells, which is the space-time curvature left by the black holes. And actually, the arrows describe the flow of both space and time. When they're nearby, they flow right in. Even space and time flows in to the space-time curvature. And when you're outside, you feel this tidal twisting of space-time caused by the spins of the black holes. All of which is encoded in the gravitational wave signal, which you can also see down here. You see the in-spiral phase, where the gravitational wave is quasi-sinusoidal. It moves up in frequency and up in amplitude till about here. At this point, we need numerical relativity supercomputers to do the calculation. So that's at that point, we look at the red dashed line or the green, which is numerically matched to the red. And what happens is that the two black holes merge together and then decay away. Then a merged black hole decays away in a ring down. So there's in-spiral, merger, and black hole ring down. By contrast, if these are not black holes, they're neutron stars, then they're composed of matter. That, and not just matter, extremely dense matter. Neutron stars are essentially large nuclei. So they're nuclear densities. In fact, they're 6 or 10 times nuclear density in the core, the most dense objects known to humanity. They are, when they come close together, they tear each other apart in tidal disruption and distortion and emit an enormous amount of matter. To simulate this on a computer, you need to simulate not just curved spacetime, but also matter and radiation, including the strongest magnetic fields in the universe, all at really extreme conditions. So we can learn a lot about not just gravity, but also nuclear physics from observing neutron star mergers. Talk more about that in a minute. Okay, I think we've already seen this slide. Oh, well, I'm going to play it anyway because I just love that last part here. So here we are zooming into two black holes orbiting each other. And here's the waveform that they're emitting. And right now we're reaching and approaching the merger, which is at the peak of this waveform. We're slowing down in order to zoom in. Now we're 0.7 we're milliseconds away from merger. And here we are at the moment of merger. And at the moment of merger, what you saw is two black holes merging into one, as described by general relativity, right about here. Actually, right about here is where I want to be. How do I get to it? Here. Yeah. Here. The two black holes are separate, are two distinct objects. Here they become one. This is what I call the kiss of the black holes. They merge and jiggle about for a while, producing a huge burst of gravitational waves. This is a supercomputer simulation. This took months to generate. By the Simulating Extreme Spacetimes collaboration, SXS, and you can go to black-holes.org to look at some of these wonderful visualizations that they have. Okay, here was our very first event that we detected on September 14th of 2015, a little bit more than 10 years ago, the first detection of gravitational waves by the LIGO collaboration. This was the signal at the Hanford detector. In blue is the signal in the Livingston detector. You can shift it by 7 milliseconds. It lies right on top of the somewhat noisy signal from the Hanford detector. We can extract the waveform by suppressing the noise in a variety of ways and modeling it. And you can see that the model, which comes from numerical solutions to general relativity, agrees with the signal that we observe at both detectors very, very well. In these time frequency spectrograms, here's time in seconds. So this is a total of 0.2 seconds, 200 milliseconds from beginning to end. And frequencies, there's a logarithmic scale from 32 hertz to 500 hertz. We see that the signal starts at low frequencies and for a very, very small fraction of a second sweeps into high frequencies. And then there's the merger, and the ring down is at such high frequencies, it's above 1,000 hertz off scale on this picture. Okay. During that time, the velocity in the orbit goes from about 1/3 of the speed of light to 2/3 of the speed of light. And the separation between the stars goes from 4 or 5 Schwarzschild radii to 1 Schwarzschild radii. And at that point, it merges. This was our first event. It was very exciting. It led to a Nobel Prize for the leaders of our project, Ray Weiss at MIT, who passed away last year, Barry Barish and Kip Thorne at Caltech, who led the project from the inception, in fact, since the 1970s and 1980s. I joined LIGO in 1998, so I've been involved in LIGO for almost 30 years. Let's look at those signals in the frequency domain. And in particular, our very first signal, which lasted only a fraction of a second in spiral, merger, and ring down. In the frequency domain, what we see is it's sweeping from low frequency to high frequency. That's the in spiral. The amplitude gets larger, but it spends less time at each frequency point. So in this spectrum, it appears to fall. And then there's the merger, which is where it flattens. And then this peak right over here, believe it or not, it's a peak. It looks more like a knee. Okay, this knee over here is actually the ring down. It's in fact a damped sinusoid in the time domain, and it is a Lorentzian in the frequency domain, an atomic line shape, essentially. And you can see it merges at about 200 hertz. Our second event, observed just less than a month later, was lower in amplitude, longer in duration. It's in green here. It merged at higher frequencies. That tells us that it was further away, but lower mass. If it's lower mass, the black holes are smaller. Because of that, they can get closer together before they merge, and they can be moving faster. So because they're moving faster, they emit gravitational waves at higher frequencies. That tells us that they are lower mass objects than the first one. And the third one, observed in December of 2015, is of intermediate distance, and but even lower in mass. It merges way up here at 600 hertz, and it is close enough that it's louder than our second event, but not as loud as our very first event. So we can tell a lot about the properties of the sources, their distances, their masses, and more by looking at the waveforms in the time domain and the frequency domain that carries all that information. And in particular, the information we can observe, here's the two detectors observing gravitational waves from a distant source in a direction n hat. Those two black holes have masses m1 and m2, but they also spin on their axis with spin vectors s1 and s2 as they orbit in an orbital plane. And here's the orbital angular momentum perpendicular to the orbital plane. So we can measure all these things. We can, from the waveforms themselves, we can measure the masses of the stars, their spins. If they're not black holes, but neutron stars, we can measure how their tidal forces will deform the neutron stars before they merge. And if their orbit is eccentric, we could even measure eccentricity. Those are the intrinsic properties of the wave. The extrinsic properties, in other words, the properties that depend on the observer, are the time at which we observe it, the phase of the orbit, the sky position, right ascension and declination, the distance. We measure distance not in light years, but in parsecs, which are 3.2 light years. But our typical distances are millions or billions of parsecs, megaparsecs or gigaparsecs, galaxies far, far away, as well as the orientation of the orbit with respect to the line of sight, so n dot L. So we measure a lot of these things, and we can measure them for each and every individual event and for ensembles of events. The sky location we measure poorly. Okay? Typical events that we observe look like arcs on the sky, stretched out, and are measured with accuracies on the order of thousands of square degrees on the sky. Our best measured event, this one right over here, which was from about a year ago, is localized to about 5 to 18 square degrees on the sky. This is in contrast to measurements of astronomical objects with optical telescopes. Optical telescopes have much higher frequency waves. An optical wave oscillates trillions of times a second, well, thousands of trillions of times a second, whereas our waves oscillate 100 times a second. Therefore, they are limited by simply diffraction. They're diffraction limited. An optical source can be localized not to a square degree, but not to a degree can be divided up into arc minutes and arc seconds, and you can localize sources in the sky to thousandths or even millionths of an arc second of accuracy. So this is many, many orders of magnitude poorer localization, and it's the best we've ever done. And that's because our gravitational waves are much lower in frequency, much longer in wavelength, and suffer diffraction much, much more in our detectors. Having 3 detectors makes a huge difference. This event was 3 detectors were on, the 2 LIGO detectors and the Virgo detector way over in Pisa in Italy. And this event is very special. Talk more about it in a bit. Okay, as mentioned in that video, these events generate, we can measure a lot of things, but these events, we can estimate how much energy is radiated. And as mentioned earlier, even for our very, very first event, the energy that was radiated was 3 solar masses worth of energy. And this was really one of the most efficient conversion of energy, of matter to energy. 4.5% of the total mass energy of the system was converted to gravitational waves in that last fraction of a second. 3 solar masses worth of energy is a truly, truly, truly astronomical amount of energy. In fact, it was the most energetic event ever observed by humanity until then. Since then, we've observed even more energetic ones. Okay. And also, as mentioned, the peak luminosity for a fraction of a second outshined the electromagnetic energy output of all the stars in the observable universe by a factor of 50. It truly was the most energetic thing ever observed since the Big Bang. And since then, we've observed even more energetic ones. Now, neutron stars, which we observed in 2017, that was the very first one, they make a much bigger mess when they merge together because they're matter, very, very dense matter. They tear each other apart. They make, well, in this awful bit of uh, of internet clickbait, it says very bad things happen. But for us, this was a very, very, very good thing. Probably one of the best things that's ever happened in my life. What happens when these two stars get close together is they start to tear each other apart. This is tidal distortion and then tidal disruption. And then a lot of the nuclear matter gets flung into space, and it can be still gravitationally bound, forming something called an accretion disk. It will be very hot and dense and form an enormous amount of not just gravitational waves, but electromagnetic radiation, extremely energetic, up to gamma rays, and an enormous amount of dense nuclear material, the kind that produces very heavy elements like uranium and plutonium that we observe on the Earth. Here's a video. Let's see if it works. Comes with a soundtrack. Here's two hot neutron stars, incredibly dense, not as dense as black holes, orbiting each other. They smash together, make a huge fireball. Those are gamma rays coming out at the poles and heavy nuclear material coming out right here. The gamma rays smash into the interstellar medium and make an enormous amount of radiation. That's an animation. And that disruption, that dynamical ejecta, powers a gamma ray burst and a broadband afterglow. It can be detected with gravitational waves and with optical telescopes, ultraviolet, optical, and infrared, radio telescopes, X-rays, gamma rays, and even neutrinos. In the case of the event that we observed in 2017, that was simulated in that video a minute ago, we detected radiation in all of these bands except not in neutrinos. It's a little bit too far away for us to detect the neutrinos from it. A closer one would be very exciting. This is called multi-messenger astronomy with gravitational waves. I'm going to skip the details. We found that new star in a galaxy 40 megaparsecs away. We saw light at every wavelength, and we saw evidence of emission from very heavy nuclear elements. What you can see over here is the periodic table, and you can see that it's color-coded by the origin of the elements. So hydrogen and helium were produced in the Big Bang. The heavier light elements like carbon, nitrogen, oxygen, and so on are produced in the collapse of massive stars, core collapse supernova. We are stardust. And the heavier elements are produced in things like merging neutron stars primarily, and that includes platinum and gold and mercury and so on, as well as and lead, as well as uranium and plutonium. The heaviest elements primarily produced by the very rare but extremely energetic binary neutron star mergers. So we are stardust, but, well, my wedding ring, anyway, is neutron stardust. Truly a different kind of thing. And my wedding ring is not from Mordor. I just bought it locally. Anyway, neutron stars are amazing objects. They are the dead remnants of massive star core collapse supernova, like neutron stars, except like black holes. But neutron stars are produced from stars that started out about 10 or 15 solar masses, and above that, they don't collapse into neutron stars, they collapse into black holes. In the core of a neutron star, all four forces of nature, strong, weak, electromagnetic, and gravity, are under the most extreme conditions that could never be studied on Earth. Far, far more extreme than what we could do in any laboratory condition. But they can be studied in astrophysical environments through the radiation that they emit in binary mergers, which is how we've done it so far. So they're amazing objects. Now I'll tell you change topics for a moment and tell you a little bit about how LIGO observes the sky. Well, we have these observing runs. Okay, LIGO actually operated in the 2000s for 10 years and detected absolutely nothing. And then we upgraded to what's called advanced LIGO, and advanced Virgo came online. And we did our first observing run in 2015 to 2016. At that point, we were able to detect gravitational waves. The sensitivity of our detectors was such that we could detect gravitational waves from binary neutron stars out to about 80 megaparsecs, which covers maybe 1,000 nearby galaxies. Okay. And since then, we've gotten better and better and better with more and more sensitive detectors. Here we are now in 2026, making our detectors more and more sensitive to binary neutron stars. Binary black holes are much more massive, like 50 times more massive. They generate much more louder gravitational waves, and we can detect them out to 10 or even 20 times more than this. So thousands of megaparsecs or gigaparsecs. In other words, to a fair fraction of the edge of the observable universe. All right, we observed for a short while in what we call our first observing run, detected 3 events. In our second observing run, we detected 8 events. In our third, we detected about 15 or 20. And in the fourth observing run, which ran from 2003, just ended in November of 2026, we detected hundreds of events. And this is very exciting for us. In the future, we plan on a short run in 2027, a much longer run with a much more sensitive detector from 2028 to 2031. At this point, LIGO India comes online and joins us, and then we stop for even more upgrades and even bigger detectors, which I'll briefly mention later. I'll skip this. So the number of events that we've observed over observing time has gone from just 3 to 11 or so, and is now up to 391. Okay, 391 events is a lot for me. I wouldn't mind having 3,000 or 3 million, and we will. It's just a matter of time. More is definitely better in this business. Why is more better? Some of you have seen a plot like this one. This is called a Hertzsprung-Russell diagram. If you've studied astronomy, you've studied it in the very beginning of your studies of astronomy. It shows stars along the main sequence. These are all stars from our galaxy, in fact, nearby. And along the main sequence, here's the sun right in the middle there, right over there, right there. And these are stars that are burning their hydrogen into helium in their core. Once they finish burning hydrogen to helium, if they're more massive, they'll start burning the helium in outer layers. You'll get red giants, and even more massive ones will burn from helium all the way up to iron, supergiants. Okay, the lighter stars like these red dwarfs and the sun will never go supernova. They will stop burning their hydrogen to helium and maybe into carbon and oxygen a little bit, and then become white dwarf stars. And there are billions of white dwarf stars in the Milky Way. But the more massive ones will collapse, and their core will collapse, leave behind either a neutron star or a black hole. But before they do that, they'll have a truly gigantic supernova explosion before they collapse. Okay, and these Hertzsprung-Russell diagram tells us about the whole life cycle of stars as a function of their masses, well, proxies, their temperature at their surface, that's the x-axis, and the luminosity, the brightness, is the y-axis, tells us about many different stars, all the different stars that could live in our galaxy, and how they live and how they die. And we want to do the same thing. The life cycle, the formation, evolution, and death of the most massive stars through the gravitational waves emitted by the black holes that they leave behind. We want to build a Hertzsprung-Russell diagram, not of all stars now, but for black holes. And also search for anything new, rare, different, or completely unanticipated from curved space, from the warped side of the universe. This is one way of visualizing our catalog, how it's grown from run 1 through run 4. On the x-axis is basically time, and on the y-axis, the distance in billions of light years now. Okay, so here's 1 billion light years, and here's 5 billion light years. And our very first events were detected. They were nearby because our detectors were only sensitive enough to detect things nearby in the nearest 1,000 or 10,000 galaxies. But now we're detecting them from galaxies far, far away, and we're sensitive to binary black hole mergers in millions or tens of millions of galaxies. Another way of visualizing it is in this very busy plot here. Let me try to walk you through this plot because it's worth it. The x-axis is time, and here's our observing runs, 01, 02, 03, 03 broken up into 2 runs. And here's the first part of the 4th observing run. We have a lot more to come. They'll all fall off this. The plot will get too busy when we add an additional 200 events. At that point, we'll stop making this plot. It'll be crazy. But what you see here on the y-axis in logarithmic scale are the masses of the compact objects, neutron stars or black holes. If they're neutron stars, or we think they're neutron stars because they have below about 2.2 solar masses, then we color them in this orange color here. Here's our very first binary neutron star, 2 neutron stars. This is the primary is the bigger one. The secondary is the smaller one in mass. They're both about 1.5 solar masses. They merged to form a final black hole of about 2.5 solar masses, which, as indicated here, might have started out as a very massive, hypermassive neutron star, but it can't support itself, and then it collapses into a black hole and makes that huge burst of energy that I showed you in that video. Here was our second binary neutron star that we observed in 2019. We did not detect electromagnetic radiation from this one. It was a little bit too far away. And here are binary black holes, lots of them, lots of them. This is a low mass binary black hole. 2 black holes of about 7 solar mass and 12 solar masses merging into a black hole that's not quite the sum of the two, a little bit less, because it emits several solar masses of energy and gravitational waves at the moment of merger. Here is one of our most massive black holes observed. In fact, this is the most massive one, 100 solar masses and 150 solar masses merging to make 225 solar masses, merged black hole, and emitting 10 solar masses of gravitational wave energy. That was the most energetic event ever observed by humanity. That was back in 2023. Another exciting day for me. And you can see lots more, and they will form some kind of a Hertzsprung-Russell type diagram of binary black holes. And they're helping us understand how these things form. In particular, we don't know how the more massive ones form because stellar evolutionary simulations predict that there should be no black holes in this mass range. And that's because they would emit an enormous amount of ordinary matter before they collapse. And so a 100 solar mass star, which is extremely rare, would throw off 50 solar masses worth of matter and collapse into, at most, a 50 solar mass black hole. And yet we see them. But most of the ones that we see are actually not produced in core collapse supernova. They're produced in a merger. In fact, in this case, it may be that this merged black hole came from the merger of 2 black holes that had themselves come from a merger of 2 smaller black holes in what we call hierarchical mergers. And this could go on. For all we know, this merging hierarchy could continue to make billion solar mass black holes, like the supermassive black holes that we observe in the center of galaxies. Maybe, maybe not. There's also this intermediate region here, the lower mass gap, which we're starting to fill with merged objects that we don't even know whether they're neutron stars or black holes because we don't observe them electromagnetically. They're too far away. We only observe them with gravitational waves, and it's hard to tell whether they're neutron stars or black holes. But there's a lot to learn as we get more and more data and with more and more sensitive detectors. We release our data to the public with very low latency on the order of less than a minute in order for optical telescopes to point in the direction that we think the source is. And this way we could catch the explosion, if it's a binary neutron star, at the moment that it happens. And we also, when we finally observe all these events, we produce catalogs. We release the data and the strain data associated with each of our hundreds of events that we observe. We call this the Gravitational Wave Transient Catalog, GWTC. We are now in GWTC 4.0, which has 219 events in it. And you can download these, you can study them, you can do all kinds of fun things with them. We have a whole open data workshop that teaches you how to use our data, and you're all invited, if you're interested, you're all invited to attend that workshop. It's free and it's on Zoom, and you can just Google Gravitational Wave Open Data Workshop. In our catalog, we can find exceptional events of all kinds. At this point, I'm sort of, I've been talking for close to an hour, so I want to finish. So I can't talk about each of these individual events and what makes them interesting, other than the fact that some of them are much more massive than we ever expected. Some of them have mass ratios. This is the primary mass and the secondary mass. This one here has a mass ratio of 8 to 1 or so. Most of them are equal masses. The way they form suggests that, but they're very unequal masses must have formed in a different way. And some of them have very high spins. The black holes have very high spins, which means they probably didn't come from the collapse of a mass of stars, but maybe they came from a previous black hole merger. So very high spins, very low spins, and so on. So these are what we call exceptional events. They're sort of, they're rare, even in our data sample, and they may tell us something about different, distinct populations of binary black holes, the same kind of distinct populations that you might recall seeing in the Hertzsprung-Russell diagram, telling us about how these things formed and what their ultimate fates are. We can, with many events, we can study the population, the whole population of compact binary mergers as a function of their masses, their spins, their redshift, which tells us how far away they are in cosmic, due to cosmic expansion, and try to understand how such systems form over cosmic time. That's wearing our astrophysicist's hat, but we can also put on our physicist's hat and ask, are these signals consistent with what we expect from general relativity, or are they giving us hints that general relativity may not be the whole story? After all, we are studying the strong field, highly dynamical regime of gravity for the very first time, and it can only be done with gravitational waves. And we study them by simulating what the gravitational waves would look like in numerical solutions to general relativity with supercomputers. And then we compare them to the data like I showed you early on. And in that way, we can see whether our events are consistent with the predictions of general relativity, or maybe they show a hint of something beyond, perhaps the first hints of quantum gravity, which is certainly possible, but we haven't seen any evidence of it yet. In fact, all of our tests of general relativity have demonstrated that the signals we observe from binary black hole mergers are entirely consistent with the predictions of general relativity. But that consistency is tested at the 5 or 10% level. In the future, with very, very loud events, we have one event with a signal to noise ratio of 80. So we did our very best tests of consistency with general relativity, and we got those tests down to percent level. So now our signals can be established to be consistent with general relativity at the 1% level. There isn't much room for beyond GR physics. But it's not going to stop us from keep looking, because it would be truly exciting. Yes, you can win a Nobel Prize for proving that Einstein was right yet again. But if you want to win another Nobel Prize, you have to prove that Einstein was wrong. So we're looking for that. We're motivated. Of course, we're not biased in either direction. We simply want to do unbiased and careful tests to make sure, to understand whether what we're seeing is due to, it can be fully explained by general relativity or not. We can also measure the cosmological expansion rate, the Hubble constant, or the Hubble parameter at the current time, and measure it ultimately over cosmic time. You may have heard also that electromagnetic radiation can be lensed, gravitationally lensed, by intervening galaxies, or really superclusters of galaxies containing lots and lots of dark matter. And you can get things like Einstein rings. In fact, that very first video that I showed at the very beginning had a distant star field being gravitationally lensed, in that case by a massive black hole. Usually it's by a supermassive black hole or even a supercluster of galaxies. That would produce multiple gravitational wave signals that look very similar, coming from the same direction in the sky with the same kinds of wiggles, but coming at different times with different amplitudes. So we look for that. So far, we've seen no evidence. It's a rare thing. We didn't expect to see evidence, but eventually we will see evidence of gravitational lensing, not just of electromagnetic radiation, but of gravitational waves. And lots more. This is a really new and rapidly changing science. So we write lots of papers on the subject, but I'm out of time. Ask me later if you like, if you're interested in our catalogs of gravitational waves, our exceptional events, exotic events that we haven't seen yet, like eccentric orbits and gravitational lensing, multi-messenger astrophysics, as well as searches for continuous gravitational waves from spinning stars and from a stochastic background, things like that. So there's lots more, and this is just a small fraction of all the papers that we've published in the last few years on the subject. So we're opening up a whole new field of physics and astrophysics with these kinds of observations. We are adding LIGO India soon. LIGO Kagra is getting better and better. So these detectors look like this. The Kagra detector in the Japanese Alps is underground. It's 3 kilometers long in a mine, the same mine that the Super Kamiokanda neutrino detector is. Should be shown here. It's above it somewhere. And it is not sensitive enough yet. They're working on it, trying to make it more sensitive. On the upper right is an artist's drawing of what LIGO India will look like in Hingoli in eastern Maharashtra. Again, 4 kilometers long, and it will be very similar to LIGO. What we want to do in the next 10 years is build even bigger detectors, which will be even more sensitive. In the United States, we have plans for something called Cosmic Explorer. These it will be an L-shaped laser interferometer, not with 4 kilometer long arms, but with 40 kilometer long arms, 40 kilometer long arms, so 10 times bigger. And in Europe, a triangular shaped object, each one is 10 kilometers long on the side, called Einstein telescope. We don't have sites for either of these two. The Einstein telescope is looking at Sardinia and Belgium and maybe or maybe Germany. We haven't yet come up with a site for Cosmic Explorer. With these detectors, this plot here is a plot of the mass, the total mass of the binary black hole system. Here's binary neutron stars down here, 1 to 5 solar masses or something. Here are the typical masses of the objects that we observe in LIGO. Here are what we call intermediate mass binary black holes. Of course, the supermassive ones are at millions or billions of solar masses. Okay, and here is redshift. Okay? So here's today, redshift of 0 is a log scale. A redshift of about 1 or 2 is what's called cosmic noon. This is when the universe was producing stars at its peak. And redshift of 10 to 20 is cosmic dawn, when the universe was 500 million years old and the very, very first stars had formed. Okay, this is what the James Webb Space Telescope is designed to look at stars way out at redshifts of 10 or 20, the most distant stars that we could imagine. At higher redshifts, early times, before the first stars, we don't expect to see any black holes or binary black holes, because black holes, we understand, come from the collapse of massive stars. Unless black holes also form via via very strong space-time fluctuations in the early universe. Those are so-called primordial black holes. And if we can detect black holes at redshifts greater than 20 before the first stars in this kind of a mass range, we will have discovered primordial black holes, the seeds of the supermassive black holes in massive galaxies. And that will tell us an enormous amount about the evolution of the universe at the earliest of times, the so-called dark ages of the universe before the first stars. On the right, you see the circle doesn't mean anything, but you see the white dots, those are binary black holes, and the orange dots on the left are binary neutron stars. And here's the redshift at which we are sensitive. So if we look, for example, at an upgrade of LIGO in green, well, actually, let's just look at Cosmic Explorer. If we look at Cosmic Explorer, we can detect every single binary black hole in the entire observable universe, including maybe primordial ones way out here, and almost every binary neutron star in the universe. That will give us a truly comprehensive cosmic census of these dead remnants of the most massive stars that helped form heavy nuclear matter, including my wedding ring, for example. So there's lots coming up, an enormous amount of physics that you can explore with these next generation, what we call third generation detectors that we hope will come online in about 10 years. Okay? So we can look forward to that, and that will be truly exciting. I actually, in the short term, very much look forward to LIGO India coming online at about 2030. At the earliest, around 2030 or 2032. That will be a truly groundbreaking moment where we will have a truly globe-spanning network of gravitational waves to help us understand these most exotic objects. So with that, I'll conclude with my obligatory ending cliche. The future of gravitational wave physics is golden. So thanks to everybody who has supported us over the years. Thanks to the National Science Foundation in the United States for paying for LIGO. It's a $1 billion project. And especially thank you for your attention. And I'll end here. Thanks, everybody.
Thank you, Dr. Weinstein, for your really interesting lecture. It covered a lot of topics, and thank you for making sense of those complicated looking graphs. I now open the floor for questions. Hello.
You have to speak louder because I can barely hear you.
Hello. I guess when.
Now I can hear you.
Hello. Anybody has questions? Anybody with questions can come here and ask your question. Dari.
Hello, sir. I have a couple of questions. So, firstly, you mentioned about baseline at the very beginning of the lecture. So, I was connecting it to radio astronomy. So, I was wondering if you can, in tandem, use multiple LIGOs together to form a bigger baseline. And if there are,
Very much so.
what are the challenges for that?
Very good. So that is, in fact, the main reason why we need LIGO India, okay, to have a larger baseline. If you know radio astronomy, you know how to use it as a phased array of antennas. And that's because the wavelengths are sufficiently long that you can resolve the oscillations, which you can't do with optical, but you can do it with radio. Radio, RF electronics, you can follow the oscillations to tens of gigahertz or even hundreds of gigahertz. In LIGO, we're at 1,000 hertz, so much, much lower frequency. We operate the LIGO antennas in exactly the same way, a phased array of antennas. We resolve the phases. The delays between the phase of the waves as detected by different detectors allows us to, using timing alone, locate the source in the sky to some level of accuracy. And then we can go more than that, not just timing, but also amplitude information to locate the source in the sky to even better. And that's what gives us our diffraction limit of at best 10 square degrees of sky localization. We can, and this works just like radio with triangulating in the sky and as a phased array. But we do more than that because our sources are binaries. And if you know, in astronomy, it's very hard to measure the third dimension, distance, with ordinary stars. Like we don't know the distances to, stars on the other side of the Milky Way. The closest stars, we can measure the distance to them using parallax, but that's just the closest stars. The more distant stars, you just can't measure their distances in any good way because they're not standard candles. Our sources are standard sirens, not standard candles. The energy falls off like 1 over r squared. That's a candle distance, but the amplitude falls off like 1 over r. That's a amplitude distance or a siren. Okay, and binaries in the radio can be measured. Their distance can be measured that way. So binaries allow you to measure distances because they have orbital dynamics that you can disentangle from all the other information to actually infer the distance. Okay? Not always perfectly, but well enough. So we can measure 3-dimensional locations of sources: right ascension, declination, and distance. The radio can only get the distance for binary type systems or standard candles or standard sirens. Our standard sirens are binary neutron stars, but we've only observed 1 of those. Does that answer your question?
Yes, sir. So also I had another doubt. Like just previous few slides, you showed a diagram which were like redshifted away. So I saw that majority of them were located at some specific redshift. Many of them are not closer by. So any reason for that uh, bias?
Oh, absolutely. We because general relativity doesn't have any special scale. It has conversion factors, but not special scale. It doesn't have sort of a signpost telling you what the energy is. A star does. A star has atoms on the surface. You can do a spectrum, an optical spectrum, and measure the atomic spectral lines. And if it's a star in a galaxy that's far away, or a whole galaxy, you can measure the spectral lines and measure how much they are redshifted from cosmic expansion. We can't do that. We have no signpost. We have no scale, like the atomic scale, to tell us how, any spectral line to tell us how much the gravitational waves are redshifted from a distant source. We can measure the distance crudely. We can assume the Hubble law and infer the redshift. And then we have to iterate because once we've inferred the redshift, we can, it turns out that the signals being redshifted tell us that the masses are heavier than they actually are. Our source masses are redshifted. Okay, that's kind of a wild thing. We have redshifted masses. Once we estimate the redshift, we can correct for the masses, correct for the distance, and remeasure the redshift and iterate 2 or 3 times until we get a self-consistent solution. So we can estimate the distance and the redshift only by assuming Hubble's law. But if we want to test Hubble's law, we have to do something else. And the something else that we can do is use binary neutron stars as a standard candle. They tell us, if we locate the source well enough, they tell us the host galaxy. The binary neutron star we observed in 2017, GW 170817, was in a host galaxy called NGC 4993, which was 40 megaparsecs away. Well, they don't measure the distance. They measure the redshift. Redshift is 0.1. Redshift is 0.1. So we knew the redshift from the optical observations. We measured the distance from gravitational waves, and then we combined them. Do you still hear me?
Yeah.
We combine them to get an estimate of the Hubble constant. Now, the Hubble constant has been measured to percent accuracy in other ways, and we measure it to 10% accuracy so far. So far, we have not really contributed to measuring the Hubble constant accurately. But in the future, with thousands of binary neutron stars, we hope to do exactly that. Does that answer your question?
Yes, sir.
Great.
Anybody else has any questions?
It's late in the day there.
It's actually night here, nighttime, around dinner. Sir, I had one question to ask you. You had shown the timeline of various phases of LIGO observing events. So every time LIGO kind of reopened, the distance at which it could observe those events increased. So I was wondering about like the technological advancements needed for that kind, like increasing the observation distance.
Very good. So as you noticed, I talked mostly about astrophysics and not about the LIGO detectors themselves. I just showed one cute little simplified video. I hope you appreciate that the LIGO instruments are immensely complex with enormous amounts of technological innovations to make things this sensitive. And I could talk for many, many hours on that subject, but I'm out of time. So I'll just quickly say that the main thing that we do is increase the laser power. If you increase the laser power, you have more laser photons, which are the transducers of space-time stretching and squeezing to laser light at the photodetector. And then you're less limited by laser power fluctuations. We're actually limited not by the laser power fluctuations, but by the fluctuations in the electromagnetic field of the vacuum. And that's quantum fluctuations. So we are, LIGO interferometers are quantum limited over almost all of its frequency band. Okay? And then we can say, well, we can't get around quantum limits. Okay, the Heisenberg uncertainty principle is fundamental, but we can fiddle around with it. So what we do is we we manipulate the quantum vacuum. Okay, the vacuum is just empty space without any laser. We can manipulate it using quantum optics, second order nonlinear quantum optics. We can produce what's called a squeezed quantum vacuum. And we can squeeze it either in amplitude or phase. Since it's vacuum, there is no amplitude, but still, we can squeeze it in two orthogonal quadratures, which you can think of as amplitude and phase. We squeeze it one way at high frequencies where we're limited by photon quantum shot noise. And we squeeze it differently at low frequencies, frequency-dependent squeezing, to lower the Heisenberg back action noise, which is fluctuations of the laser power on the mirrors that physically kick the mirror around by fluctuating radiation pressure. So these are the two limits of quantum noise, quantum sensing noise. This has been known for 50 years. We have learned in the last 5 or 10 years how to actually manipulate that quantum noise, make it different at low frequencies and high frequencies, and thereby improve our quantum limits. We're not evading quantum limits, we're manipulating the quantum limits to our benefit in what we call frequency-dependent quantum squeezing. I could talk for hours about this. It's a phenomenally fascinating and interesting thing. If you are interested in it, this is what we do in LIGO India, and I encourage you to learn about it and get involved in LIGO India.
Yes, sir. Thank you, sir, for all your wonderful answers and the really exciting talk. I end this talk here, and yes, thank you, sir. Thank you so much for joining us.
It's a pleasure, everybody. Have a great rest of your evening and hope to meet some of you someday soon. Bye-bye.
Bye. Thank you.